I have been working in the research lab of Dr. Kate Detweiler. This lab is part of the anthropology department at Florida Atlantic University. My project is titled Facial Recognition of Hybrid Monkeys. Thank you so much for joining me today. In 2008, Dr. Detweiler invited me to join her research lab. After many years of research and fieldwork, Dr. Detweiler had discovered and documented a previously undiscovered new species of monkey, hybrid Cercopithecus monkeys. Incidentally, it's only the second new species of African monkey to be confirmed in the past 35 years. So, certainly, a very exciting research and academic achievement. In general discussion, we refer to this new monkey population as the hybrid monkeys. This is due to the fact that they are a hybrid of two species of monkeys, red-tailed and blue monkeys. Dr. Detweiler's research is primarily located at Gombe National Park in Tanzania. You may be familiar with this park or heard of it before, as it was made famous by Jane Goodall as the location where she pioneered her behavioral research conducted on the chimpanzee populations in the park. Dr. Detweiler has been conducting on-site research in Gombe National Park for many years. Her work with the hybrid monkey population is ongoing and providing new information as research projects continue to develop. One problem facing Dr. Detweiler and her research team was an inefficiency with identifying monkey individuals. This was due to low-resolution photos and a lack of telephoto lenses, along with a steep learning curve for new field assistants and researchers. Basically, when a researcher arrives in the field, there is a time commitment to learning the characteristics of each monkey so that any specimens or behaviors can be properly attributed to the correct individual. Time spent learning to spot an individual could be better utilized to further the research projects and, furthermore, better identification can eliminate the errors in research caused by this problem. Dr. Detweiler was interested in developing a system to identify the individual monkeys through AI and machine learning. For this reason, she asked me to join the research team and to begin work on this aspect of the project. This is to give you a bit of an idea of the area where our research takes place. Gombe National Park is located in Tanzania, in the western Kigoma region. Accessing this national park is not simple and requires several plane rides and a lengthy boat ride if you are starting from FAU. Due to the remote location of our research, we had to consider how to create a useful and convenient user interface with the further knowledge that the internet access would not be guaranteed to the field researchers. More on this later. In order to fully understand what the researchers were up against and the scope of the problem of identifying the individuals, I traveled to Gombe in the summer of 2019. There are many purposes for this visit, and among those was creating a larger library of high-quality, clear images with a telephoto lens to assist with the building of the AI portion of this project. In order to teach a program to identify the monkeys, I needed a large sample size of images for training. I spent 2 weeks at the field research site with Dr. Detweiler and her team, photographing the monkey population to ensure a large quantity of images for each monkey individual, and to make sure there were high-quality images available for me to use. The field team continues to add to the collection of photos, and, even now, there are researchers in Gombe. This field research also helped me better understand the challenges of identifying monkeys. It also gave me insights on how to prepare for what the machine learning program would need to be able to recognize, as well as how the scientists were identifying each monkey today. Overall, it was invaluable to understanding the research taking place in the field and how an AI machine learning program would be utilized. This trip allowed me to build the foundation for the project. So, As I began to try to build a tool that would be of use to Dr. Detweiler, the first step was figuring out what didn't work. I quickly learned that existing human facial recognition programs didn't work on monkeys. That would have been a very simple solution. The good news is, artificial intelligence, AI, and machine learning, ML, technologies have advanced to the level at which a program can be developed and a model trained to accurately identify individual monkeys. So, with the photos we collected, it was possible to train a system to accurately recognize the monkey individuals to allow proper researcher identification and, therefore, accurately attribute data to the correct specimen. Identifying individual primates is difficult for most people and takes time to accurately learn how to do so. Field researchers have turnover, and there is a constant influx of new people who struggle with accurately identifying individuals. Inaccuracy in identifying monkeys leads to misattribution of data points, lowering the overall accuracy of the data. Upon visiting Gombe National Park in Tanzania, I saw firsthand the challenge of correctly identifying monkeys and how it could create inaccuracies in the data the researchers were gathering. As you can see from these small images, identifying the difference between monkey individuals is not easy for the untrained eye. Add to this the complications of the monkeys being on the move, very fast when they want to be, not always looking directly at the researcher, high up in a tree, you get the idea. The human eye is not a reliable system of identification on its own in this scenario. We needed AI. Now, to train our system to do the identification work for us, the first ingredient was a large data set of pre-classified images. This was so the machine could better learn the proper classifications. Our data set consisted of over 16,000 identified images composed of 62 different monkeys, which gives us an average of 261 images per monkey. 12,800 images were used to train the model, while 3,200 images were used for validation. Our initial attempt at training the machine learning program resulted in only an 80% success rate. In some areas, 80% might be considered pretty good, but when you need to know what monkey individual you were working with, 80% just isn't close enough to be sure. To assign research data, we were going to have to work harder. It seemed that part of the problem of training the program was these small monkeys, generally high up in a tree, were not any easier to photograph than they were to identify by sight. Improved equipment, better lenses, and more photos had only gotten us so far. The program was looking at an image with a small bit of monkey and quite a bit of other material, mostly leaves, sticks, branches, etc. So we came up with a new hypothesis, that if we were to crop the images to just the face of the monkey, we would eliminate a lot of the confusing parts of the message we were providing. We assumed this would improve our identification accuracy. I don't know about you, but the thought of manually cropping thousands of images wasn't appealing. Plus, I was deep into learning about computer vision and machine learning. And, eventually, the project goal was to create something the field researchers, or ecotourists, could use on their own. So, the program would have to become smarter. Surely, there had to be a way to teach the computer how to identify what the face of the monkey looks like. Of course, there were many. So, basically, our solution: create a different AI machine learning algorithm to identify and crop monkey faces. First, hyperlabel was used to manually label 1,000 images. Then, I had to pick out what platform I would use to train how to identify and crop out monkey faces. I ended up selecting a system called YOLO. It stands for You Only Look Once. Why did I choose this platform? Because it was fast, really fast, and because it gave me an excuse to learn about another facet of AI machine learning: object detection. A YOLO V3 object detector was then trained over 4,000 iterations to identify and create bounding boxes over monkey faces. With this system, we achieved 95.9% accuracy of bounding boxes. We then applied the YOLO V3 object detection to detect faces and crop all 16,000 images, which only took a couple of minutes to fully process and, more importantly, gave us a way to identify monkey faces in the future. It worked, and it got rid of all those pesky sticks and leaves and other background noise, and let the algorithm focus on the faces, which, by the way, was what the best research assistants in the field were doing. They would talk about facial coloration, the shape of the nose, the shape of the face, the distance between eyes, etc. So now you can see all those adorable monkey faces. Much easier to see what we are working with when we are down to the cropped image. So we moved along to training how to identify individuals using FastAI. Why FastAI? Of all the systems I looked at, they had the best online curriculum and tutorials. That was important, as I was teaching this to myself. The first tutorial I took taught me the fundamentals of identifying breeds of cats and dogs, and was easily transferable to what I wanted to teach the computer. A big thank you to FastAI community for not only building such a great platform, but making it accessible for people just getting started with AI. To train on the FastAI, we tried various models as starting points, including ResNet 34 and ResNet 50. We utilized Google Compute AI machine learning optimized computational clusters, which are 200 times faster than CPUs for doing this type of training. Also a big thank you to Google for giving poor students like me sandboxes to learn and create in. I later learned that our university offers high-performance computing access as well, and will take them up on that as I continue my journey. So on to train the model. We had 16,000 images to work from and pulled 20% of the images out to create our validation set, leaving 12,800 to teach with. Using ResNet 50 as a starting point, we trained the model over 4 cycles, which resulted in an error rate less than 4%. This was way better than the 20% error rate we were seeing without cropping the faces. Plotting the learning rate, then unfreezing the model and training for 3 additional cycles resulted in a final error rate of less than 1%. I always smile when I look at these tables, but it looks like the entire project was completed in less than 15 minutes of compute time, which, while technically true, I can guarantee you it took me a wee bit longer than that to get it to this level. Now we are much happier to discuss the results of the AI machine learning system. At this point, the result of this project is the creation of an AI machine learning monkey facial recognition model that can correctly identify an individual monkey with 99.44% accuracy. That number moves the needle much closer to the accuracy level we needed to confidently assign research data to the appropriate individual monkey. The eye chart to the right is a confusion matrix, plotting the predicted versus actual monkey. And while you may need your own computer vision algorithm to see the tiny font, what it shows is extremely little confusion by the algorithm. Finally, we had to make the 2 trained models usable and useful. A web application was created which enables end users to take or upload a photo of a known member of the group. The system will use the YOLO object detection to find and crop the face, and then pass that onto the FastAI model for a probability distribution of what monkey it may be. In the slide, you can see just such a real-world image. This photo is uploaded, the face is detected, and, in this instance, you get a 99.9909% chance that this is Hope you're studying, and a very, very small probability it could be Elsa, Twin, or Limo. I intentionally used a responsive user interface that would work well on mobile devices. This will be the real asset to Dr. Detweiler's team moving forwards. Researchers in the field can snap a photo and find out right then in the field which individual they are dealing with, eliminating or at least greatly reducing the probability of misassigning data. Who knows? Maybe someday eco-tourists visiting Gombe could use my application to instantly pull up background and facts about the monkey they see. Having been there myself, I can tell you that the experience changed my life, and it's something I wish I could share with all of you. Here are links to the websites for the tools I used: FastAI, YOLO, and Hyperlabel. Here are some of the published papers I used in my research, and as references. All research builds upon a foundation created by scientists who have pioneered, discovered, and shared the knowledge that creates a starting point for the next generation. For this, I am grateful. And finally, I would like to thank and acknowledge the following agencies and individuals: Tanzanian government agencies COSTECH, Tawari, and TANAPA, Drs. Anthony Collins and Deus Mungugu, GSRC, GHMP Field Assistants Mary Inkorgawa and Mineo Mapango, Charlene Foreigner assisted in building the photo collection and provided quality check on identifications, project photographers Charlene Foreigner, Sarah Crawford, Mineo Mapango, Nuhu Buki, the Department of Biological Sciences at Florida Atlantic University, and the Department of Anthropology at Florida Atlantic University. Go Owls! Thank you so much for your time and interest in our project, Facial Recognition of Hybrid Monkeys. I have enjoyed sharing this and hope you enjoyed it as well. I am available for any questions. Thank you.